First, we explored cob and straw bale construction. Then we designed a working industrial building that heated and cooled itself. In our third experiment to improve energy efficiency, we put our ideas to work for a modern home.
In order to be any good at actually building these things, we have to try them. We have to put our life where our mouth is, essentially.
The ARC, as it became known, is 4,000 square feet of living space, a home in every sense, forever busy with family gatherings and grandchildren. Yet it is unlike any home you will find anywhere. The formula for this home makes it one of a kind.
Our house, sort of like the Manny shop, has a lot of solar capture area and a lot of greenhouse on it, which is also solar capture area. Very well insulated and has a lot of thermal mass.
Super insulation in its walls and its ceiling, windows with a full 12 inches of dead space between them, solar panels heating the household water. A greenhouse that doubles as a water processor, using living plants to clean the home's gray water. An oversized garage that stays warm all winter using no heat source whatsoever. And like the Manny shop, the building is anchored on top of a bed of heated sand.
The ARC sits on an underground box that's made out of 10 inches of foam. And inside that insulated box, we fill it with 2 feet of sand. And then we covered the sand with concrete, and the concrete is heated with hot water that flows through embedded pipes. So essentially the concrete floor floats on an insulated box of dirt. Unlike the
Manny shop, the ARC does not use solar energy to store heat under the building. That's done through transference of the in-floor heat. In other words, the warm concrete floor slowly warms the sand. It takes about 3 days to fully warm up the box under the house, but thanks to heavy insulation, the sand retains its heat for a long time.
The heater consists of just one water heater element out of an electric water heater and a pump. Just the fact that in January we can run our furnace 1 day a week gives you a hint of how well it keeps its heat.
It takes just $54 a month for the electricity to heat and cool this spacious home. During the milder weather of spring and fall, body heat and light energies all the heat that is needed. That is far below the energy efficiency required for a Minnesota Green Star home. The 12-inch thick foam-insulated panel walls created an interesting opportunity for windows, allowing us to take advantage of the natural insulation value of dead space. 2 double-glazed windows, one on the exterior of the building and one on the interior, have proven an enormously efficient way to eliminate heat loss from windows. It turns out that 2 double-glazed windows cost far less and performs much better than a good triple-pane window.
The wisdom is that the spacing on windows, you get the best R value at someplace around 3/4 of an inch, and then you don't gain much after that, or it actually goes down really slow as you widen up that space. We found out that that's under certain test conditions, and in the real world, there's a lot of times when the extra space actually does pay off.
The 1,000 square foot garage is in itself a model of energy efficiency. It's often studied for its potential as an inexpensive single-room efficiency home. It has no heat source and no insulated thermal mass, yet it stays relatively warm even during the coldest winter months. Garage temperatures stay in the mid-50s during the winter and low 80s during the hottest part of the summer. A late but interesting addition to the ARC is a water processing experiment, which has helped turn the house ultra-green and keeps it humid during the long winter months.
You're actually walking into a sewage processor of sorts. This is our greywater processor. This takes all the water out of the bathtub and the washing sinks and the laundry, and it all gets dumped into here, which is a 300-gallon gray water tank. And the water is actually rather gray.
Dirty water slowly trickles through a series of 120 30-inch trays, a total of 312 feet, containing hundreds of houseplants.
In these stacks we have little clay pellets that are just full of air holes, which means there's lots of room for lots of bacteria in there. And underneath those pellets we have activated charcoal granules. And 1 gram of activated charcoal has the surface area of a whole football field. They absorb almost all the impurities out of the water. And then the plants have their roots that tease all those impurities off of it again, and they sort of recharge the charcoal. I love the smell of the mint. The mint is invasive, it takes over. The root mat gets this thick and fills up the whole tray, and that just soaks up the water and has tons of surface area. And I swear the mint all by itself cleans it up. This is the water that comes out of the plants, and it is crystal clear. We sized this thing to handle a normal household of 4 Americans. And that's about 75 gallons per day per person. So we sized it to handle about 300 gallons a day.
Like the first 2 buildings, the household laboratory known as the ARC was not cost-effective. It was time to take what we learned and turn it into something the average contractor or homeowner can use. In the next video, you'll see how we transferred everything we learned to create an ultra-efficient home that heats and cools itself at a cost of about 10% higher than the average Minnesota home of the same size.